Hello, JuliaCon. I'm Mo Kayali, a graduate student at the University of Washington, Seattle. I'm visiting you today to talk about the library I developed, QuasiStableColors.jl, for graph compression. This is a work with my advisor, Dan Suchu. And I'm excited to tell you about how we developed a new graph coloring approach that lets you approximate important problems like max flow, linear programs, and centrality. So let's get started. So I think to this audience, I don't need to sell graphs. Graphs are this fundamental building block of the work we do, right? They are seeing increased adoption, they're increasingly applicable, right? If you've had a Spotify recommendation, that recommendation is almost certainly powered by some graph-based recommender system, right? And they're increasingly large, increasingly complex, right? So if you have something like a Microsoft academic graph, that's got on the scale of 1 billion nodes. And because graphs are so ubiquitous, we've developed lots of measures over time, like maximum flow and centrality, between the centrality, that are important for a lot of real-world modeling tasks, right? Tasks like traffic modeling, landmark detection, fraud detection. However, the problem is, despite these large graphs and this importance, the scalability of a lot of graph analysis methods remains quite poor, right? So here on the slide, I show you runtimes for the Julia implementation of Brandis's algorithm, and it really doesn't scale, right? The runtime is reasonable for something on the order of 1,000 nodes, but once you get to any reasonable scale, 100,000, you're outside the realm of interactive data exploration, right? You really are outside the realm of any kind of reasonable experimentation. And this is nowhere near the largest graphs and the typical graphs that a lot of practitioners use. Cool. So my pitch today is I want to talk to you about a library, right? Available now that you can use, called QuasiStableColors. The reason you might want to use this library is it's an implementation of this graph approximation approach we've developed at the University of Washington, which lets you achieve a 10 to more typically 100x speedup if you can accept some error in your application, right? So we see an average error of about 15% on a lot of benchmarks, where as long as that's within a tolerable parameter, and for a lot of these problems like traffic modeling, that's absolutely tolerable, right? You would absolutely take that to get some kind of interactive or reasonable speeds. Cool. The work I'm about to show you, I'm going to focus today on the actual library, the underlying theory, and the experiments are in this paper to be presented at VLDB, the Very Large Databases Conference, in August. So you're always welcome to take a look at that if you're curious about the details. I'll talk mostly about the interface today and the high-level ideas. If there's time and interest, we can talk about the algorithms too. Okay. So the library has a API that looks something like this, right? You feed it between a centrality problem, a linear optimization problem, or a max flow problem, and you give it essentially a tolerance, right? How much error you're willing to tolerate, and you get an answer. But to understand how to use the API, let's talk a bit about what this coloring is. So here's a graph you might have seen before. This is Zachary's Karate Club from a famous paper in the late 70s. Every node here is a person. This is a social network of students in a real-life karate club, right? Members of a real-life karate club. And the edges are social links or friendships. And we have something like 34 students, 34 people, and 78 friendships. Now, what you might do is you have a graph like this, right? You could use the library, right? You could call this QColor function. You feed it the graph and some tolerance, and what you'll get back is coloring for every vertex, right? So, and I'll say for this audience, when I say coloring, don't think proper vertex coloring, right? Don't think something like related to 3SAT. This is much closer to color refinement, if that rings a bell. If it doesn't, well, I'm glad you're safe. But the way to look at these colors, right, is I give two nodes the same color if the distributions of their neighbors have the same color, right? Allowing for a fudge factor defined by Q, right? So if we look at the green nodes, right, you'll find that the green nodes have the property of having always a link to the orange nodes, right? Whereas, for example, the orange nodes don't have links to other orange nodes. Okay? If I am to write this more formally, maybe this would help, right? Quasi-stable coloring is a partition of the nodes, right? Such that the following property holds, right? For any two nodes within X and Y within a partition, the number of neighbors of any other particular color is within a small factor, right? A small fixed factor. And if you color a graph this way, and I'll talk about how we actually color the graph, what you end up capturing essentially the local and not so local structure of the nodes. So famously in this graph, Zachary was able to find which way the club split using MaxFlow. But actually, and I swear I didn't rig this, the club has two leaders, right? If you look at the colors, can you identify who they are? Yeah, that's exactly right. So because the leaders in the club have this very kind of unique place in the structure, right? They're going to know a lot of students. The students are in green. Those are the numerous nodes around the periphery. And it seems the club officers get these other intermediate colors, right? Yeah. Cool. So the idea here, right? Classically, these kind of color refinement techniques have been used for isomorphism testing. That was kind of the most famous application. But here, we want to use them for something very different. So the trick is we want to do dimensionality reduction using these colors. So take your initial graph, whatever it is, color it with some quasi-stable coloring with a tolerance you want. And then from that, we're going to group all the nodes with the same color into one supernode. And once we do that, we have what you might call a lifted or quotient graph, right? Where we have supernodes, the edges reflect those guarantees, right? They're labeled with those guarantees that we have for every pair of colors. And we can use that for our algorithms. Now, the key thing that really makes this work and makes this interesting at all is we find that for three applications, right? MaxFlow linear optimization between the centrality, running the algorithm directly on the full graph is approximately similar to running it directly on the compressed graph, right? So for each problem, you construct the compressed graph carefully using some statistics you calculate for each color, and you can run it directly and not lose too much precision. Okay. Now, some of you might be asking, hold on, Mo, am I missing something? Linear optimization, that's not a graph, right? Well, there's this kind of cool work in about 2016 by Martin Grohe that shows if you consider matrices as a bipartite weighted graph, right? And apply some of these coloring techniques to them, the answer you get by compressing that is exactly the same as the answer you'd get for the full system, right? The catch with that work was you could not really practically compress any real matrix, right? Any matrix you gave it would decompose, would compress into itself. So what we do here is we allow some fudge factor, we introduce some error, and I'll show you it works much better on real graphs. Cool. One catch I'll introduce, and we show this in the paper, right? Finding these colorings is hard, right? So you can always trivially find a coloring by giving every node its own color, and that's a perfect quasi-stable coloring, right? Because there's no error in any partition. But that again is the kind of the case where the coloring degenerates and you don't get any compression. Now, finding a good coloring, what that means is for a fixed error, right? If you allow a fudge factor of plus or minus 2 edges, right, or plus or minus 2 edge weight, finding the coloring that has the smallest number of colors is NP hard, right? So, and if you try to dodge this by making the colorings relative rather than absolute error, same deal. You fall into the same trap. Okay. So what we do is we develop a heuristic, right? A heuristic that seems to compute pretty good colorings. Okay. Any questions so far? Good. All right. So for the experiments, what we did was we found a bunch of benchmark data sets, right, for betweenness, centrality, maximum flow, and linear programming. And you can kind of see the scale that we tested on from a few thousand nodes up to about 3 million, right? And importantly, these data sets are real, right? So they have noise, they have, yeah, exactly. Cool. So kind of the slide where it shows what kind of the trade-off is. This is the importance slide if you want to use this, right? Is this one. And the way you want to read this is, if we focus on the top figure first, right? I'm showing you the speed versus accuracy trade-off. So on the x-axis, I have the runtime as a percentage of the baseline, right? So 1.0, that's 1%, or 100x speed up, right? And here I'm counting, of course, both the time taken to color the graph, compress it, and run the algorithm on the compressed graph, okay? Now, on the y-axis, for A and B, you see relative error, right? So the lowest possible is 1.0. You get exactly the same answer. And for example, 1.2 is a 20% relative error. For the betweenness centrality, what I'm showing you is the correlation between the ground truth answers and the compressed answers. The best possible score is 1, of course. So for example, a 0.95, that's a 0.9 Spearman's row. Cool. So what we find is across these different tasks and across the sizes of the data sets, right? You get very favorable compression at 1% of the runtime, right? 100x. Across all of these, the average error is about 12, 15%, right? And what's really cool is if we now look at the lower graph, I'm showing you the same y-axis, but on the x-axis, I'm showing you the number of colors we've had to use, all right? And recall these graphs are quite large, right? They're in hundreds of thousands, typically, of nodes. And what we find is using just no more than a few hundred colors, you can really capture the important parts of the structure for these specific problems, right? And here I'm showing you the kind of the estimates, the best estimate from this method. The paper shows also we establish bounds, right? There's upper and lower bounds for the errors, but those are not implemented in the library yet. Cool. Any question about? Please.
Does the runtime include the coloring?
Yes. So the ratio you're seeing is coloring time and the compression time, and running the algorithm on the compressed over just running it directly on the full graph. Yeah. Of course. Yeah. Thank you.
The number of colors in the runtime, how do they relate there? Is there like is there a one-to-one?
No, it's not necessarily one-to-one, right? Just because the algorithm involves making some decisions based on the color, right? So it's an iterative algorithm. You start with one color and you start refining.
How do they relate more or less? Like, relate 5 colors, what's the runtime? 35 colors runtime?
So this will really depend on the size of the graph, right? So coloring a graph with 1 million nodes with 5 colors is much slower than coloring a graph. But to just give you a ballpark of the numbers, maybe that's what you're asking. We're talking for a graph with 100,000 nodes, the ability to give 10, 15 colors in several hundred milliseconds, about 500 milliseconds, I'd say. Yeah. So it's fast enough that you can do stuff at interactive speeds, right? And another aspect I really enjoy of this approach is it's iterative, right? So it's an anytime algorithm. You can either refine until you get a particular error that you want, or you can choose to stop at any point, compute the problem then, and then if you don't like the answer, if it's not good enough, you can just continue from where you paused. Cool. All right. Anything else for these results? Good. Okay. So one thing I wanted to show is for a few data sets, the kind of compression ratios and the runtimes. Oh, maybe I should have showed you this slide, actually. So here we have the runtimes and the compression ratios for various values of Q, right? Q is that parameter that controls the maximum error between any two colors, right? So that means if I have a Q of 100, there's some partition where two nodes have a difference of 100 of their edges into some other color, okay? And as you might expect, across these graphs, so if we look at DBLP, right, that's a graph with about 300,000 nodes. If you use the prior approach, which is not allowing any error whatsoever, you get almost no compression whatsoever, right? The compression ratio is only 1.35 to 1, right? So you have 300,000 nodes, you only get 200,000 colors. But with our approach, what you do is you start at the highest error, say 64, right? And you refine downwards. And you can choose to trade off runtime, right, for compression. So if you really need maximum error of 8, you might wait 2 hours. But if you can do fine with 32, you might stop at 20 seconds. Cool. Sweet. And you can kind of see where even though we bound the maximum error for our sort of theoretical guarantees, the average error, right? The average error is much smaller between two colors, right? So for DBLP, if we look at Q equals 8, right? The average error is 0.06. So between any two colors, right? Say the red color, if you look at two nodes in the red color, the number of edges they will have into green will differ by, on average, 0.06 edges. So the average performance we see is quite a bit better than the bounds require. Cool. Now, one thing you might ask is, sure, this is cool, right? There's this one technique that can accelerate a bunch of applications. How does it compare to the domain-specific approximation, right? Because if I'm a sort of domain expert, I'm some kind of analyst, I might be fine with just using the, I only want to do max flow. I might use something just for that, or only centrality. So the, if we look at centrality, we compare in these slides an approximate algorithm, the RK algorithm for between the centrality, to our approach, right? So the way to read this is at the first half of the figure. Each row is a data set, right? And then the columns are grouped by the error bound that you're demanding, right? So if you want an answer that's 90% correlated with the ground truth, that's the runtime in seconds for our method, and the approximation specific to between the centrality. On the rightmost column is the exact runtime of Brandeis' algorithm, the kind of classic algorithm for this problem. And what you can see, right, is on these data sets like astrophysics that have, if I'm not mistaken, on the order of 10,000 to 100,000 nodes, we can get you an answer that's 90% correlated in 100 milliseconds. Whereas to get any answer with the exact method, you'd have to wait 200 seconds. And even with the other approximate methods, you're never waiting less than a few seconds, right? And we find as you get more and more demanding, right, of the quality of the approximation, the advantage starts to really show, right? So at 0.97, we can get you an answer, for example, in astrophysics within 2.5 seconds. You'd have to wait a minute for the prior approximation that works specifically for between the centrality, and much longer for the exact answer. For linear optimization, and I'll say the caveat, of course, here is we tested with open source solvers, right? We tested with Tulip, Julia's Tulip, and its kind of early stopping features. It lets you stop the problem early and get a not necessarily optimal answer, but close enough. And what we find is while we can consistently give you an answer for a particular relative error value, very often the early stopping method for the solver will just time out, right? It'll time out at 20 minutes. Whereas we can, for example, if you insist on a relative error of 50% at most, give you an answer within 15 seconds. And of course, compared to a much longer solving time for the exact answer. Cool. Any questions here? Sweet. Okay. I might skip over this slide. It's just to show that the coloring is robust. So you have a particular coloring, and you start adding noise. So maybe the graph changes a little bit over time. The coloring will be able to adapt, and it won't experience this degeneration that some other approaches have. Cool. Okay. Since we have about 5 minutes left, I might just recap here. So find the implementation on GitHub. There is tutorial, documentation, all sorts of good stuff hosted on the official docs. There's some notebooks for you to play with. All the experiment code is open source. You can also access it, install it, of course, with that command. And if you have potential applications, if you use MaxFlow or centrality, similar problems in your work, talk to me. I'd love to find potential applications for this. Well, I'll stop here and take questions.
Questions? We had a few. I have one myself. So you can solve this cool problem to compress the graph, and then you can operate on the graph, and the approximation is related to applying the function on the original graph, right? Have you thought about potential ways of, if you wanted to update the compressed graph, could there be ways of doing that, or is all of the information lost in the process? Because it'd be really cool to say, I compress the graph, I can run my super optimized version on that algorithm, and if someone comes in and wants to update the old graph, I have a way to stick that information into the new compressed graph.
Thank you, that's a good question. If I understand correctly, you're asking, do I need to keep the full graph around to do updates? Or can I do my deltas directly to the compressed graph, right? So, yeah, thank you. So you would be able to do updates to the compressed graph. The issue is you'd want to amortize it somehow, right? So you could do small deltas, but the quality of the coloring will degrade over time, right? And this is kind of what this graph here was showing, right? This is inserting into the compressed graph